Lab 3, Black Hole. Introduction: to correctly calculate the mass of an unknown object, calculate the forces acting on it, and their directions was the focus of this experiment. The purpose was to relate mass, velocity, parallel and perpendicular forces, Newton's second law, and F-net of all forces, and also allowed the students to use a computational model to represent these forces. So, for some of the fundamental concepts used in lab were velocity, F-net parallel, F-net perpendicular, centripetal acceleration, gravitational force, and centripetal force. Brief overview: this lab demonstrates that the weight of the black hole is 9.75 times 10 to the 38th kilograms, and one of the ways to escape the black hole is to set the speed to 2 times 10 to the 8th meters per second, which is less than the speed of light. For the lab, the procedure was to open the starter code using the givens, calculate the mass of what the black hole could be, using that calculation, go into the second code and input the mass of the black hole, and play around with the second code to determine how fast the spaceship must go to escape the black hole. So to find the mass of the black hole, started off with the givens of the mass of the star and the gravity, and if we look to the right, we can see the gravitational force needed to be set to the centripetal force, and overall had to isolate m, and we got, in order to find the mass, we had to do radius times velocity squared divided by gravity, and from there we used that to determine what the velocity could be at given points. So to move forward, we didn't know what the radius was, so we had to estimate based on what the code gave us. And after we got all of the numbers, we took the radius and the velocity and the gravity, put that all into the r times v squared divided by g equation to get a total mass of 9.75 times 10 to the 38 kilograms. So to put this all into the code, it was a lot, but some key pointers here was setting the initial to the p initial to the star mass times the initial velocity, and for the p final to the mass of the star times the final velocity. If you go on, there's more, and where F-net of the parallel component is equal to the change over time of the parallel component. Here are also the error scales that we had to use, where the error scale had to be scaled up a lot to represent the vectors because we were working with such large numbers. And then part 2, don't crash. We had to set the speed of the ship to be 2.9 e to the 8, and the y was 0. And the error scale was once again really high, but this gave us a result where the spaceship did not crash into the black hole. What does it mean? In this lab, we were asked to determine what the parallel and perpendicular components were. These components determine all the forces acting on the black hole and the stars. The difference between the rate of change of momentum is that the change of momentum focuses on velocity and how and where the objects are moving, while parallel and perpendicular components take into account the change of momentum. That is not their sole purpose. They take into other things as well. What if? Well, I'm not too sure what exact initial velocity of the spaceship we would need in order to enter some sort of orbit around the black hole. I would say in order to find this number, we would need to set the gravitational force equal to the centripetal force, and that number would give us the initial velocity needed for the spaceship to enter an orbit. Possible errors. This lab was definitely tricky, so I think a lot of my errors might have came within the actual code itself, just because I'm not really, that's supposed to say GlowScript, not Java or Python, my bad, that I'm not really comfortable with using, so there were a lot of unclear numbers working with. And in conclusion, we can confidently say that the weight of the black hole is 9.75 times 10 to the 38th kilograms, and to escape the black hole, we need to set the speed of the spaceship to 2 times 10 to the 8th meters per second.